Let's see an example of an application of linear regression model. Some studies suggest that excessive use of social media has a negative impact on people's lives, both emotionally and physically. To investigate the latter, meaning the physical impact, a sample of 15 teenagers were studied, and their weights and their hourly use of social media per week were recorded. The weights are converted to overweight rate. Negative means underweight and positive means overweight, as you see in the table on the right. We want to investigate whether there is a relationship between being overweight and using social media. So we can actually use the correlation formula to find whether there is a positive or negative or any relationship between being overweight and use of social media. The formula is, as you see here, the covariance of x and y divided by the standard deviation of x multiplied by standard deviation of y. If you plug in the numbers and for this formula, you're going to get approximately a correlation of positive 0.84. So that's a high correlation actually in a positive. So this kind of approves, based on the sample, it kind of approves the study. And means that, yes, it seems to be a positive correlation between being overweight and the use of social media. Part B of the question asks to describe the relationship using a linear regression model, the relationship between being overweight or obesity and the use of social media. So to do this, we're going to actually do it in Python as a project to apply a linear regression model to feed into data. So you need to do some step before moving forward. You need to download the files. You need to download the data file, which is the social media txt files, and also two IPython files, the linear regression model template and the complete version. And also you need to open up the template IPython file and follow along as I do this project. Follow along with me and write the codes. So we're going to do these following steps. We're going to import required libraries and the data file. Then we're going to navigate the data and compute the correlation. And we're going to also visualize the data. All right, so we're going to start with importing the libraries that we need. Import numpy as np, import pandas as pd from matplotlib, import pyplot as plt. Okay. Next, we need to import the data that we need. The data set is called social media. It's a text file. I already have it in my workspace, so I don't need to use any address. So I'm gonna use the pandas read table, and I'm gonna put the data in my data variable. pd read table, the name of the file, social media txt file. I want to take a look at the data. We can use heads, but the data set is small, so I'm gonna see all the data. So this is the data. It's a table with 15 entries starting index 0. The first column is social media hourly used, and the next one is the overweight score. Negative means underweight, positive means overweight. Okay, next I want to see whether there is a correlation between these two variables, between the social media usage and the overweight score. So I'm going to use the function from NumPy called correlation coefficient or CoCoef. So before I do that, I want to put the data in two different variables, independent variable and dependent variable. So independent variable x is equal to my data, the S media, that's what it's called here. The column is called S media, the next column is overweight. So I put the S media users in X variable, and Y is going to be my data overweight. Okay, so now I'm going to use the pandas coef. So I'm going to print out print correlation equal to, and use the numpy core coef for X and Y. Right, so this is the output. One is the correlation between social media and social media, of course, is 1. The correlation between social media and overweight is about 88%. The next one is again the same. It's the correlation between overweight and social media. So it's a matrix that's considered the correlation between combination of these. Okay, so what we need to know is that the correlation between the social media usage and being overweight is highly positive, about 88%. So next, I want to visualize the data. I want to visualize the social media as the x-axis variable and the overweight score as y-axis. So before I do that, I want to specify the x-axis and y-axis. So the x label, I want it to be social media hours, or hours of social media, and I want the y-axis plt y label to be overweight score. Okay, now I want to plot the data, so that would be plt plot x and y, and I wanted to use a circles to show our data points. So I'm going to use O, and then I'm going to ask it to show the plot to us. This used to be a problem. This has to be in, yes, this has to be in. Okay, yes, this is our plot. So this is our plot, the hours of social media on the x-axis, and the y-axis shows the overweight score. To split our data into test dataset and training dataset, so that we can use the training dataset to train our algorithm, which here for the linear regression model means to figuring out the coefficients of the model, which are the intercept and the slope. So let's import the train test split function from the scalearn model selection, import train test split, and now we're going to split our data to train and test. X train, X test, Y train, Y test equal to train test split. We're going to give it our data X and Y. If you don't specify it, by default, the train test split is going to split your data into 75% for training and 25% for test. But I want to use a bigger bulk of data for training. So I'm going to specify that using this, using the test size equal to 10%. And so that we get, all of us, we get the same output, I'm going to initiate the random state to 0. Okay. Next, I'm going to we need to actually reshape the X data that we have, X train and text test, because right now it's a single array, and if we don't reshape it to a multi array, we're going to get an error later on. So I'm going to do that. So I'm going to reshape xtrain and xtest and put them back together in the same variable name. Xtrain equal to xtrain values reshape into an multi-array, -1 and 1. And I'm going to do the same for the test dataset. Xtest values reshape right. Next is the model development. We want to develop the model. So let's import the linear regression model from the scikit-learn linear model module, from a scikit-learn linear model import linear regression. Linear regression has L and R in capital, so make sure that you follow the spelling, otherwise you're going to get an error. Okay. Also, to evaluate the performance of the model, we need to import the R score, as you know it from statistic R score. It's called the R2 score, and it's in the metrics module. So from a scikit-learn metrics import R2 score. Okay. So now I want to define a model based on the regression model that I have. I'm going to pick a copy of it, and I'm going to call it my reg model, my regression model, and that's a copy of the linear regression. And we can actually fit the function, our model here as well, where we can fit our training data to the training data. So let's do that using the fit function. And I'm going to give it the X train and Y train. All right. So our model is now trained, meaning that the algorithm has already figured out its coefficients, the intercept and the slope. We have trained our model, so we have already figured out the coefficients, intercept and the slope. So let's take a look at those. I want to print out the coefficients. Print the coefficients. I'm going to start with the slope. Print slope equal to, and here my regression model, and coefficient 0. So this is going to, it has actually an underscore here. So the coefficient is about 0.887. This slope. Now let's print out the intercept. So the intercept is equal to my regression model and intercept underscore. So the intercept is about negative 22.59. All right. Now let's make a prediction using our model. I'm going to call the prediction ypredict. Ypredict equal to, and I'm going to ask my model to make a prediction. My reg model, the function is predict, and I'm going to give it my x test. So it made a prediction based on the x test for the y values and put it in the ypredict. We can now actually take a look at the R score. So print R square equal to, and then R2 is score of, I'm gonna give it the y test, the actual values, and our prediction, ypredict. R square is negative 1.43. Sometimes R square can be actually negative. It might surprise you, but that's true. So to show you that the behavior of our model can change, I'm gonna go back here and change the data split, for example. So I'm gonna, instead of 20%, 10% for test size, I'm gonna use 20%. Then we have to rerun all of this back again to recreate the model using the new parameters. So the slope is similar, the intercept is similar as well. Our prediction, R score is 67%. So now it's positive. So we can actually, as you see here, what happened here, I assigned a different size of data for training and test, and that totally changed, actually not totally, but a little bit changed. Actually, if you look at what changed here, is the slope is a little bit changed, the intercept is a little bit changed, and we have now more test data to make a prediction on. So this helped to change the R score value. All right, let's now visualize our model and our prediction. So I'm going to plot the data, plot PLT plot, and I'm going to plot the X and Y using little circles. Okay. And then I'm going to plot the regression line here. Just plot a line if the prediction of our model was perfect, which is not, all over the circles data, the data point would fall on the line. So let's plot the line, PLT plot X test and Y predict. And so this is going to plot a line, and I'm going to show the output. Right. The reason that we have actually these parts of a line and it's not a complete line, it doesn't cover all the data point that we have, is these lines actually just plotted for the test data, and test data right now I set it up to be 20% of our data set, so that's why it's partial. And we could actually make it longer if we use different partitions of data for test data. All right, so you can just imagine the rest of this. It's gonna go to the this point here, right here. And as you see here, our data points, the circles, have not been fallen on these lines. So that shows that our prediction or our model is not perfect, and we didn't expect it to be perfect.